So what is a race condition? So whether your program runs correctly or not, obviously you want your program to do something, right? And whether it outputs or it does what you intended it to do, the correctness of the program, if it depends on how the threads are scheduled, in which order they are scheduled, right? And how the scheduling is interleaved. If it is dependent on that, then we say that there is a race condition. A race condition exists. And when you run your program, the race condition may happen and it may cause a problem or it may not cause a problem. So let's see some very, very simple examples of race conditions. So let's start with very simple case where you have processor 1 and you have processor 2 and you have a shared variable x, and both these processors want to increment this shared variable x, right? How does a processor typically increment a shared variable? So you will say load x to R1, right? So you're loading x into register R1, and then you say add 1 to R1, right? So you're adding 1 in the register, and finally you will say store R1 back to x, right? This is a set of 3 instructions that are required in order to increment a variable which is in the memory. This actually points to some location. Maybe this is location 1002. So this will also be location 1002, which is nothing but the address of x in the memory, right? Okay, so this is what thread 1 wants to do, and what does thread 2 want to do? Thread 2 also wants to do the same thing. So it wants to say load into some register, maybe let's say R1X, add R11, store R1 back to X. It's pointing to the same address. Alright, so how do these instructions get executed? Right, so if you have, let's say, 2 processors, each one of them has their own register set. Now what will happen? So the first processor, let's say that it loads the value of R1 into its register, right? So what is the value that will come to processor 1? So whatever is stored over here. So let's say that initially the value stored over here is 0, right? So processor 1 will fetch 0 into its register. And now let's say that it is executing add R1 to 1. So this has nothing to do with the memory, right? It's just incremented the value of the local variable to 1. And then it stores R1 back to X. So it overwrites this 0 with 1. And then thread 2 comes along. It executes the instruction load R1X. So what will happen here? This value 1 will be fetched over here in processor 2. 1 will be added to it. It executes add R11. So this will become 2 and then store R1X. So it's going to store 2 back to the memory location. Right? Everything is fine. So let's say I was trying to count the number of occurrences of, let's say, a word in a document, and I split the document between processor 1 and processor 2. So each one of them were counting their own words and they were updating, right? So this is, let's say, the number of times that the word exams appeared, right? So processor 1 saw the word exams 1, so it tried to update the variable x, which is the location which is keeping track of the number of times that the word exams appears, right? And then processor 2 also saw exam 1 and it also tried to update the same variable, and eventually you got 2, and there were 2 occurrences, you got 2 in the final variable. So everything seems fine, right? If any of the processors now tries to print the value of x, you'll get the value 2, which is what your program intended to do, right? But now what could have actually happened is something different, right? Here is another alternate thing that could have happened. This is your variable x. So let's say that first thread 1 loads R1 into x. So what will go to thread 1? The value 0. Let's say 0 was stored over here first, right? And it executes add R11, so it updates this to 1. Now before it can execute store R1x, let's say that processor 2 invoked load R1x, right? So what will happen? It will fetch the data from this location, and that data happens to be 0. And then it executes add R11, so it updates this to 1. And now let's say that processor 1 executes store R1X. So this comes back and it writes 1 over here. And now processor 2 executes store R1X. So it's going to overwrite this 1 with 1. And now the output is incorrect. That's not the output that you wanted, right? So the correctness of your program is dependent on how the threads are executing the instructions, right? In which order they executed in the instructions, or how did the memory see those instructions being executed, right? If the memory receives this set of instructions, this load and this store first, and then it sees this load and this store, you will get what you desired, right? But if it sees this load followed by this load and then maybe one of the two stores, then the answer you get is going to be incorrect. Okay, so this is a race condition, and race conditions are very, very common when you're working with multiple processors, when you're working with parallel programming, or even if you're working on a single processor with multiple threads, right? Because the threads can get scheduled because of time slicing or because they perform some blocking operation and they get scheduled out, right? We discussed this last time.